Yeah, we give out data here. Right, we're actually live, so let's not embarrass ourselves. Last week, we were talking about predicting other matrices, predicting networks, testing hypotheses. And part of that involves, particularly in dyadic cases, it involves correlating matrices. So I thought I would actually go back to the larger idea of correlating matrices and then get to QAP in particular, and those tests that are called permutation tests. And then we would also do a little bit on clustering if we have time. Since the last time we did that, we did a lot on characteristics of groups and then used those to find groups, but we only did it very quickly. And so I thought we would spend some time on that. So I want to show you a data set that's kind of fun. I'm going to display it, and it's called NewFrat. And we have touched on it briefly before. But NewFrat is the data set that was collected by Ted Newcomb in the 50s and wrote a book about it in the 60s. And it's about 17 people who are living in a house. And what he does is he puts an ad, there's an empty house by campus. He gets control of it. He puts an ad in the paper and says, you can live in my house for free as long as you fill out a survey every week. And part of the survey is a network survey. And so every week we have everybody's feelings about everybody else all the way through the semester. And as you know, there was spring break, so there's a missing like week 9 or something, week 8 to week 10, yeah. And it's kind of a fun data to play with. The only problem with it is that back then everybody was consumed with rank order data, which means that every row has the same set of numbers. Everyone's got a 1, a 2, a 3, a 4, all the way. And you can't tell like whether somebody's got more friends than somebody else, because everybody's got a first and a second and a third. So we'll just have to live with that. Also, you have to remember that the numbers are backwards, so that a 1 means their favorite person, and a 16 means their least favorite person. That's probably not going to bother us, although just to be sure, I'm going to avoid any errors of interpretation by recoding these data. And to cement that we have both a command line and a menu system, I'm going to use the command line because it's just so convenient, and say something like nuke equals reverse of NewFrat. Let me see if I can make that bigger. I can at least make this what I type bigger. The rest of it doesn't seem to change. So that says, go find a data set called NewFrat, take the reverse of it so that what was a small number becomes a large number, vice versa, and then put it into a new data set called nuke. Okay, so I do that, and I press enter. I'm having a little trouble. Press enter, there we go. And by the way, I don't know if your machines say this running time thing. If they don't, they do, okay. You can turn that on and off by saying timing on or timing off. If I do timing off, then from now on you don't see the running time. I happen to like the running time. So now I could display nuke, and it's got the 17 matrices. And I happen to remember that the very first one, he had a 1 somewhere over here, probably right there, 13. It's now become 16, which is the largest possible number. Okay, so these have all been reversed. So bigger number means like the person more. Now, I want to look at the pattern of change over time. And the obvious thing to do, in my view, is to correlate whole matrices with each other, which I can do in a lot of different ways. One of them is by going to Tools, Similarities and Distances. Tools, Similarities and Distances. And here I'm going to put nuke, which is a new data set. I'm going to do correlations, but not between columns, not between rows, but between entire matrices. And then I say OK. And I get a correlation matrix. So each row and each column is a period of time, is a week. And that 0.646 there means that the correlation of the social structure in week 0 with week 1 is 0.65. Pretty high, meaning that things didn't change that much in the first week. Although, it's not super high. The first week, they didn't know each other at all. So they'd been together for 5 days, and they formed some impressions, and then another week happens, and you correlate them, and there's bound to be some change there. This 0.646 here, I was rounding. Compare that number with the correlation between the 14th week and the 15th week, 0.899. So from the 14th week to the 15th week, nothing changes in terms of social structure. Everybody who liked each other before likes each other still a week later. So actually the big change was the first week to the second week. Now look at the first week to the third week. It's a little bit lower. First week to week 3, I should say. It's labeled week 3, is 0.548. It's getting smaller, smaller, smaller. The social structure is wandering away from its starting point. Getting more and more different. You can see there's a very clear decline there, but the decline is slower at the back end. In those last few weeks, it doesn't change as much as it does the first 3 weeks, as you might expect. I have no specific number to look for. I'm just seeing the pattern. Yeah, I'm noticing that this first row, the numbers keep declining, but they don't decline as much towards the end. At first, you can go from 0.646 to 0.6 to 0.548, but after that, it's a very small change. Plus, it bounces around a little bit. That's right, yeah. It's like if it changes just 10% from week 1 to week 2 and another 10% from week 2 to week 3, it just accumulates over time. Yeah. But the one difference is that, that first week 1 to week 2 is only 0.6. Then it's 0.8, then it's 0.85, 0.84, 0.88, 0.9. So in other words, week to week change is bigger later on. Is bigger earlier on.
So I wonder if just the difference in the change there is greater than.
I think so, although the data were always collected on Fridays. So that week 0, they had actually been together for 4 days. They had a few days, yeah. And, you read these like Fast Company types of articles that say people decide who you are within the first 3 seconds. And these are directed. So it's saying that, say, the correlation 0.6 means that if A liked B a lot this time, then A will like B the second time, regardless of whether the reverse is true or not true. Okay, now, we can get a lot out of this by studying this closely, but visualization almost always helps. So the clear method for visualization for this kind of data is almost always MDS. So we're going to do a multidimensional scaling. And to do that, we go to Tools. And we'll do Scaling Decomposition. Oops, I already chose non-metric MDS. That was a little quick of me. Tools, Scaling. Non-metric, I happen to find that it works better. We can talk about the differences if we like. And the correlation matrix, I no longer remember what the correlation matrix was that we just produced. The last file created was nuke, P for Pearson, M for matrices. So this is correlations. It's Pearson correlations among matrices. That's the one we want. The number of dimensions. Well, the only number of dimensions that we're going to be able to visualize are 1 or 2. So let's go with the 2. The data are similarities, meaning that the bigger the number, the more close we want them to be on the map, the more similar they are. So I say OK to that. And I get that outstanding pattern for just a second. And then we come back to it. So I just wanted to say this page here gives us the coordinates of each week in space. And this stress number tells us the extent to which it had to distort the data to fit it into a two-dimensional representation. And a 0 would be perfect. 0.03 is excellent. Less than 0.12 is just fine. So that's perfectly good. Now we look at our picture. And what do we see? Well, what we see is that week 0 is quite a bit different from week 1. Week 1 is quite a bit different from week 2, but not quite as different as the first one. Week 3 is different, but not quite as big as the last gap. And there's a little bit of a larger gap in here. Then right around week 5, 6, 7, 8, 9, 10, 11, they're all identical. Nothing much changes to the social structure there. It like reaches stable. But there is a gradual moving that's systematic. See, in here, maybe there's some random change, some how do you call it? The kind of change that you see in eddies in water. It's kind of just moving in lots of different directions. But then you start to see a little bit of systematic change. It's not much, but it's moving away from its week 8 period. And then finally, there's kind of a slight change again to week 15, which actually brings it closer to some of the earlier weeks. So these are kind of the periods of change. It's there's a long process of change at the beginning, and then relatively speaking, relative to all this stuff at the beginning, of course, all of the end stuff is just the same. But even within that, we capture little bits of evidence of changing going on. The X and Y axis in an MDS is arbitrary. So it doesn't have any kind of meaning, and it's not oriented. Well, it's actually oriented in such a way that the biggest variance is left and right. The only thing that's being captured here is that two nodes are close to each other to the extent that they are highly correlated. And two nodes are far away, like 0 and 15, to the extent that they are uncorrelated or negatively correlated. But otherwise, there's no interpretation to the map. No, yeah. Although it does look amazingly geometric, doesn't it? It's interesting. We could look at this also from a net draw point of view. We could pretend that the correlation matrix is a network, strength of ties. So I'm going to try that. I'm going to go to the CLI, and I'm going to draw nuke dash P dash M. That was the correlation matrix that we had created. Nuke dash P dash M. And this isn't too illuminating because there tends to be a line between every pair of nodes. I mean, even between week 0 and week 8, there is a non-zero correlation, so it puts a line there. But we could change the definition of a tie. We could, for example, right here in this box over on the right, you see a tie is considered anything greater than 0. So if the tie strength, if the correlation is greater than 0.2, well, that didn't change much. What if it's 0.4? Well, we lost a couple of things. It's actually easier to go to this thing called the increment down here. Make the increment 0.1, or for some of you, it might be comma 1. And then hit the plus sign. That'll increment the 0.4 by 0.1, and then hit the lightning bolt, and then the plus sign, the lightning bolt, the plus sign. Too many. Let me go back. The lightning bolt. I could make my increment smaller now. Make it 0.01 and increment more slowly. I prefer to have most of it connected. So this is a network diagram of the same thing. There's a line between 2 weeks if the correlation is greater than or equal to 0.84. So these are correlated at 0.84. These two are correlated at 0.84. But week 2 and week 4 are not correlated at 0.84. It's below that. Up until you get to about week 5, and then everything starts looking more or less the same. Yeah. So this is a marvelous method for looking at change in networks, and would be especially interesting if there were some kind of event that went on somewhere in there, a reorganization, and then you see whether in fact people's informal ties changed as a result of that formal reorganization, or any other kind of event. I have a data set. Unfortunately, it's only 5 points in time, but at the 3rd point in time, they introduced a technology change. And in that technology change, some of the people that used to be sort of on the outskirts became more central because they understood how to use the new technology, which was Excel, by the way. Big technology change. But so everybody started going to them for advice, and some of them decided that they liked each other, and it kind of just changed the social structure as a result of that technological change. Yeah. Yeah. So obviously you could do the standard one, which is just use the people that were there the whole time. The other way, though, is to create a matrix in which it's got all the people that ever existed, and then for the times that they weren't there, they just have all zeros there, or missing values. And then when you correlate those will be missing for certain years, but will be present for others. And the MDS will like that just fine. It will have no problem with that. And the same with the network one. So ideally here, particularly looking at the MDS, and going back to, actually we have to run it again. Let me just run it again. I go to Tools, Scaling, Metric MDS. It seems like it would be just so great to know something ethnographic about what was happening each week, and to see, was there something that would lead to this kind of linear, very slow, very slight moving away here? If we had something to correlate that with, it would be great. This is friendships, yes. Yeah. And he wrote the book. This is reproduced in his book, The Acquaintanceship Process. So it's on campus, so these are students. They're all male, and it was an empty house that he said you could come and live in. And so they lived in the house and they interacted. We call it the fraternity data, but it wasn't actually a fraternity. It was just an empty house. Okay. Questions about that? So that's the idea of being able to correlate matrices. Yeah. Well, an easy one to look at is how much do you interact with. So how much do you interact with each of these people? And changes in interaction patterns are often tied to certain things, such as moving physical locations or changing job functions, if it's an organization, something like that. But it really doesn't matter what the relationship is. It could be physical distance. It could be emotional support that you feel that you get from the other person. It could be anything that we normally construct ties from.
Like how often do you meet to discuss a particular issue?
Yes.
And how that changes over time?
How much do you talk to this person about health issues, for example? And then we'd see how much it changes. In this case, of course, we're not looking at the individual level. We're looking at the entire social structure. But we could also look at the individual level in various ways. What might we do? Well, I don't know if this is going to work or not. I haven't tried this. So let's suppose that we put in nuke here. We do Pearson correlation, and we do it by row. So, yes, okay. So there's going to be one for each time period. All right, so I think what this has done is that it's looked at the first row, so that's a given person, person one, and looked at all the people that they like and don't like, and compared it with the second person. And so this person one and person two, have not very similar likes and dislikes, okay? Person one and person four have very similar likes and dislikes, 0.457. And some of them are negative, like 14. Whoever a person one likes a lot, 14 doesn't like a lot. Okay? Now, we could look at that 0.457 and see, what does it look like at time 2? Oh, it's lower. What's it look like at time 3? It's even lower. So the alignment between person 1 and person 2 is diverging over time. And we could look at that separately for each person. Let me think about this. Let me try something first, and then I'll explain it. So let's call it Y. I don't like the way it cuts off the bottom of the letter, though. That's hopeless now. Y equals transpose of nuke by column and level. Display Y. Okay, now let me see what I've done. It's just like writing. You don't know what you think until you've started writing something. I don't know what I've done until I've typed it. So still don't know what I've done. I can see the main diagonal is here, and then it moves down to here, and then it'll be in the third one, it'll be here. What am I trying to do? Oh. Let me try one more thing here. Display transpose nuke by row and level. That's what I did, isn't it? I did column and level before. Okay. So I think now what I've done here is for person 4, I have their attitudes towards every other person across week. So person 4 liked person 2 pretty much all the way through, except that they're slightly declining over time. They like person 1 increasingly over time. Let's see, how about 17? Everybody loves 17. Yes, person 4 loved 17 pretty much all the way through. That didn't change. Person 16, big favorite in the first week, declined almost immediately, but then picked up a little bit, but then sort of a decline after that. Okay. So we can see each pair of persons' pattern of likes as it goes over time with every other person. That suggests we could also do something more simple, a little easier to understand. Let's look at popularity over time. So that's, right now I'm looking at, that's just person 4's view of each person, and this is person 3's view of each person. But what if we look at everybody's view of each person? So I'm going to say something like pop equals, first I'm going to say d nuke, so this is dichotomized nukem, equals dichotomized nuke less than or equal to 3. Now what that means is I want to create a new file called dnuke. That's the inside here. That's a dichotomized version of the nukem data, which is this up here, such that whenever the value of the tie is less than or equal to 3, it's going to be a 1. Oh, but nuke has already been reversed. So let's not make that mistake. So we'll make this greater than or equal to 3. So if the person is in their top 3 choices, call it a tie. Let's see how that goes. I'm going to leave this and come back in to see if it cures that ugliness. No. Yes, you're right. So that was dumb too. My God, how many dumb things can we do? So for display dnuke, it would be 1s everywhere. That was crazy. That basically meant if you liked them in the slightest little bit, let's go to call it a tie. That's not at all what I intended. So I'm going to go back to the original matrix because I understand that one. And so I'm going to say dnuke. I wish I could make this small. Dnuke equals dichotomize of the original matrix, new frat, less than or equal to 3. Now let me make sure I haven't fully confused everybody. The original data was called new frat. It was organized in such a way that it was rank orders. A 1 meant my favorite person, 2 meant my second favorite, 3 meant my third favorite. By dichotomizing it less than or equal to 3, I'm only getting the top 3 choices for each person. So I hit enter, and then I can display dnuke. And there we go, very few 1s. For each row, it's just the top 3. For each row, the top 3. Okay. So now I want to know how popular is everybody across time? So I could try to sum up across, well, how could I do this? How can I figure out how popular people are across time? Looking for ideas from somebody. Yeah, so I want to sum it up. So suppose I did that. Suppose I did something like XX equals total of dnuke by column and level. let me try it and then I'll explain it. Display XX. Okay, that kind of worked. So let me go back here and look at this command. This is a total command. It's like sum in Excel. It works three-dimensionally though. And I'm going to take my dichotomized data and I'm going to sum it up separately for every column. And I'm going to do it for every level. And every level here is a week. The result of that was this. So here we have at week 15 how popular each person is. Person 17 got 8 mentions. Person 15 got 0 mentions. In week 14, person 15 had 1 mention. In the last week, the one remaining person that liked them decided they didn't like them. Person 17 still had 8. So I found what I wanted. The only thing I don't like about it is that it's across multiple different things and it's not all in one matrix. So I'm going to make what is currently different matrices into rows. And I know I can do that by saying transpose all of that rows with levels. And if I do that without mistyping, because there is no such thing as star total, and I display XX, I now have at week 0, that 2 means that 2 people put number 1 in their top ranked people. 5 people put number 4 among their top 3. 8 people put number 17 in their top 3, and 8 people put number 11 in their top 3. Notice what happens to 11. 11 was very popular in week 0 and does something ridiculous, maybe gets an inflated ego and then treats everybody badly and nobody likes him after that. Person 17, many people like them in the first week and continue to like them, actually peaks at week 5 with 10 people and then continues to be well liked. Person 16, never well liked. 15, never well liked. Person 9 is a popular one, yeah. And in a, no, I don't know if it's an increasing pattern. I guess not. Yeah. Goes up and down, yeah. There's a certain stability later on. Person 4 is also one who, yeah, you know, they're quite stable at medium of the pack, and then things start bouncing around. They go from a 3 to a 6 to a 1 to a 2 to a 5 to an 8. It's like now they're like experimenting or something. It's like, I'm going to behave differently and see what happens. Yes. Okay. So the first thing I did was to sum this thing up. And what do I mean by this thing? Let's just check what I have. I have dnuke. And dnuke is the 1-0 version of who likes whom at every point in time. Now I want to take the sums of the columns. And why the sums of the columns? Because that's how many people, that's who likes that person, right? So I want to know how many people like that person. So let's say I call it my sum equals the total of dnuke by, now, sorry if this is a long-winded version, but I just want to do this. What if I say just by column? What will happen is I will display now my sum, and it will simply add up across all weeks how many times somebody said that they liked 17. So across all weeks, and 17 people, 125 times was 17 chosen as like a top friend. That's not helpful because we can't see change in time. We can at least, though, see overall liking. 9 and 17 are clearly popular figures, and 10 is not, 3 is not. So what I did wrong was, I'm pressing the page up button or the up arrow button to get back to this previous command. was to say, yeah, sum it up for columns, but also break it out by level. I want it separately for each month. This is something like a pivot command in Excel. So if I do this, and now I display by sum, I get the in degree for each person for each week. Now, the way UCINet thinks of this is that this is a three-dimensional matrix. And the dimensions are that it has one row, 17 columns, and 17, actually, is it 17? And like 16 levels. 15 levels. There's 15 weeks. That's how it thinks of this matrix. That's not the most convenient for me to have one row per level. I'd rather have it just be one level and 15 rows. So I can simply interchange rows and levels. The way I do that is I say popularity equals the transpose of sum by row and level. Oh yeah, it's my son, isn't it? Thank you, my son. By row and level. So that's going to interchange the rows with the levels. So now there's going to be 15 rows and only one level. In other words, in the matrix, it's a pop. Now, I don't know whether to say that that's advanced. I guess that's advanced. What it really reflects is familiarity with some of the tools in UCINet that handle data sets as three dimensions, and you can look at them this way or this way, and you can squish in different ways. If I had done, by the way, the total of nuke like this, I get one number, 34,000. It just summed up every single value in that big three-dimensional matrix. If I said display the total of nuke by row, it would do it for every row. And it's the same for every row because these data are like that. If I did display the total of nuke by level, that's actually useful. Well, not in this case. But it gives me the number of ties in every week. Because these data are artificial, the number of ties every week is determined by the researcher. But imagine if I had said I could get the density that way. Display the average, the within matrix average nuke by level. That would give me the density for every that would give me the average number of ties per week, which is always 8. So three-dimensional manipulations of the data. Now, I just want to go back to I don't know if I save this or not, the transpose of my sum by row and level. If we were going to build a model of this, what might we do here? What's to be explained here? I think of the data like this. See, what we've got here is time as an x-axis, right? And what we've got is a number of profiles. And some people, well, we don't have time as a profile. Actually, time is not the x-axis here. Now that I think about it, I think we should change that. Sorry. Yeah, I think it would be more natural if we, I'm going to save this here. There's an easier way to do it, but now that we're here, I'm going to call this x equals, and then I'm going to display the transpose of x. Yes, that's more like what I had in mind. So if you notice, the x-axis, the horizontal bit, is time. And the vertical bit is different profile. So we have person 17. And here, this is in degree. And we have some people are liked by 0 people, by 1 people, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Most you could be liked by is 15, 16 people, everybody but yourself. And if you notice, 17 has a profile that looks something like this. They're like that. And it's a flat profile way up here. So that's person 17. And person number 10 has a very interesting profile. They do this. So they not only are low in general, but it's declining. Person, I don't know who has a different profile from all of that. Well, 12 has an interesting one in that they kind of vary at first. They're like starting at 6, they go down to 2. There's 12 again. They last, they go up a little bit, they go up quite a bit. They're around there. And then finally, at around 5, they figure it out. And they're stable. It's like, okay, I understand these people now. That's person 12. Who's the person who oscillates? Maybe person 4, kind of going wacky. It's almost the opposite. Start out level, and then they kind of go like that. So there must be somebody else who has an increasing profile. I think. Not really. Yeah. Not really. But you could imagine somebody that does this kind of thing, right? They start out low, but they keep increasing. So you could characterize each one of these profiles, right, by 2 characteristics. One is the overall trend. I mean, the overall level, I should say, not trend. And another by the angle. So in effect, what you could do is you could regress their in degree on time. So suppose we did in degree equals B0 plus B1 time. And we did it for person 17. So for person 17, I'm going to record the results over here. For person 17, their B0 and their B1. Their B0 is going to be high. It's going to be approximately the average, right? So it'll be, I don't know, 7. Their V1 is going to be 0. They don't really go up and down. They're just flat, like that. Person, was this person down here? Was it person 10? Person 10 could run their regression. So this is in degree for person K. And this is for person K. Here. And this is the V1 for person K. This is the V0 for person K. So we could run this separately for all 16 people, separate regression. So for person 10, we run a regression. Their overall value is very low, like at 1.2. And their V1 is negative, -1. We could do this for all the different people. And now this now creates a data set of values for each person. We know their gender, we know their age, we know personality characteristics, and we can correlate it with their beta 0 and their beta 1. What do you think might predict their beta 0? How do you even, what do you call the beta 0 for yourself?
Intercept.
Sorry?
Like essentially an intercept. Sorry, I'm taking like multiple regression right now, so.
Yep.
Yeah, it's essentially an intercept. So when, like, I guess time would be 0, essentially that's how much in degree that person would have at time 0.
Yeah.
We don't really even have, I mean, we have 0, but you said that was after, what, 4 days of them talking to each other,
Mhm.
so.
What we predict that at time 0 with more people, maybe, I don't know, what year in the college they are, or what are they studying? If they study, I don't know, something that's popular.
It's popular, right. Yeah. What were you going to say?
Sorry.
Or it could just be a correction term.
I have a cold.
Oh, okay. All right. I'll avoid that corner. But the intercept is loosely, highly related to the average that they have on Y. Right? So in general, if somebody has a high intercept, that means that you can see, in general, person 17 was highly rated. Everybody liked them all across time. So this is a kind of overall likability, right? Their overall likability.
No, that's their start point.
It's going to be their value.
Yes, average.
It's their average. Yeah.
Or you can say V1's got a 0 for the in degree. I mean that correctly?
Yes.
Okay.
So, and that's saying that there's no slope. It's not going up. It's not going down.
It's just staying steady.
It's staying steady at around a high level. So, so this is intercept. This is slope here. And a high intercept means
My understanding is that people behave differently in different situations. So if we are just a match, I behave in a way. And then if we know each other for a long time, I behave in another way. So this is the time we just match how I behave will influence how people perceive me. Then gradually my anatomy turned out.
mm-hmm.
Then people start, okay, just start figuring out, okay, this person is different.
But yeah. Mm-hmm. Well, with a slope of 0, it also means it's kind of the last impression as well, right? It's just the overall value of these. I mean, just look at person 7's scores, right? They don't change, and they're just high in general. Now, why would some people just be liked? Doesn't matter what we think. Right. It's like, okay, so we might.
Characteristics that are not related to the context.
Yes, right, yeah. So the kind of stable characteristics, stable traits, they are extroverted, happy people, I don't know, whatever it is, tall, you said.
I mean, it depends on,
Irritating comment.
it depends on the culture, right?
And it depends on the culture. It's like whatever this culture, and these are a bunch of college-aged men in, I don't know where in the United States, so it's some particular culture.
Maybe like person captures bias, right? We're talking time here. Yes, that's bias.
Okay, so which actually could be all these things. Yeah, you just look at them and kind of go, yeah, they're cool. Now, what about B1? But remember, we're building a database here. So we're building a database, and here we've got Pearson. We've got 1 through 16, 17 actually. And we've got age, and we've got personality, and we've got B0, and we've got B1. So they're just additional variables now. And we said, well, we might predict B0 using some of these kinds of things like how tall they are. What might predict their slope? What might predict that somebody declines over time and somebody else increases over time? Something like that, right. They might have all the initial characteristics that like you think you would like, but after time you start to know them and they're kind of like, always, I don't know, they're always like wanting to know whether you like them or not. They're neurotic, and so after a while you get tired of that. And so you get a downward slope. So it could be that neuroticism predicts a negative slope. Yeah.
And that'd be a nonlinear relationship where if they're having a few interactions, it might be, oh, our relationship's getting better, but if they have too many
Right.
interactions,
There could be a downward. And that could explain some of the patterns that we see here where there's this ebb and flow here. That's going to be more complicated than a nice, simple linear regression to predict. We could just add a quadratic or we do something. But anyway, let's pick a variable. What would explain, besides neuroticism, increasing slope? More and more people like you over time. I mean, you think about the situation, it's like 17 people thrown in together, they don't know each other. They start to get to know each other.
Maybe trust.
Trust? Like what?
So you don't know each other, you're in college, and someone has access to friends, parties, girls, you name it. It's more advantageous to one.
Somebody just had girls, they just had girls. They went to the store, there was a surplus one day and they bought them. Now,
they have a lot of sisters.
yeah, they have a lot of sisters, okay. Right. Yep, that's a good one for me.
Do they share, like, they have to take care of this place that they're living in? Do they have duties?
Yes.
Conscientiousness, maybe?
Yeah, something that over time starts to develop. Because the girls thing might be, I mean, maybe that's the secret 17 popularity. It's always providing beer and girls. So I don't know. I was looking for something like, what if B1 was predicted by something like emotional intelligence? And whereas other people don't improve, this person keeps watching every interaction, realizing this person likes this and this person doesn't like that, and they get better and better at interacting with every single person in there.
You mean they're more adaptable?
They're more adaptable. Yeah, which is another way of saying they also they're high self-monitors.
But it's all ranked data, right? So it's like if an individual is maybe even like staying stable in their interactions with other people, but somebody else really acts horribly, or a group of people act horribly, then that person looks like them. Because everybody
Yes.
else went
mean, we're looking at the actual data, so we can see whether or not it's a relative thing or an absolute thing. But yes, you're right. And there's also the issue of what happens if this thing starts to break into groups so that each one has its leader. Everybody from this group hates that person and vice versa. And so the change over time is mostly a function of the interaction between the groups than it is the individuals. It could be something like that. Right, okay. So I'm going to switch now to, from the individual level to correlating matrices, predicting matrices over time. And, but since that's a little bit of a switch, let's take a break, and then we'll come back. And try to think about any situations where you might want to predict something. You want to know, how do you do it in a network context? I'm going to try to find something to erase my error. I think that will spread more. We need a clean towel.
You've already started collecting data, but I see
Right. So, I mean, I'm sure you surveyed Borgatti and Andy. So the survey style, like your data, it's like,
Yeah, so I want to,
which isn't ideal, but it's big
just,
the big thing.
I can do that.
So I'm looking at like, I've got advice, success. I mean, I've got more than this, but for this project, I figured advice, success, and friendship network with a whole bunch of attributes, you know, special area of specialization, stuff like that. So, I mean, this is all brand.
Yeah.
It's, I mean, the method.
just hang on.
I'm gonna go with
Here's the back. I mean, I've got like 7 pages
say
of
Vanderbilt.
background stuff, and I've got this one laid out. But honestly,
A lot of
like
it is
this,
pretty common
yeah.
to put the name.
And I mean,
A
I
lot
don't
of
think
very
this
few
necessarily
or else if they put in, they put
to
in.
this particular.
It'd be easier to do that.
Right, because it really just depends, like, do you have your specific, like, hypotheses or research?
Well, I mean, I figure basically
On
like,
that, do you want,
I
if they had 2 schools that
out
got
the
for
for
example,
people with higher.
how do you want that? You want them, I'll put them 2, they want 2 different.
Correlated.
I'll put those 2.
So I'm just trying to measure that I sort of.
Yeah, okay, perfect.
And
So
which
you're
is the
essentially
thing.
saying real time works more on higher centrality of evidence by output, because that's just one measure of type of centrality, so you're saying that essentially if you're more central, then you more important, but just as evidence by that measure.
Right, or organizational support as, correlated to that, for the people who have more outbreak maybe are.
Not necessarily, but I would think the more individual.
Yeah, right, exactly. So I mean, I would just.
Yeah, I was just saying, that's one of the hard part is finding the time.
I know,
Just
but.
saying, I'm in the lab like 20 hours a week, so that's why I'm
You're
like,
good.
running
Alright.
So next
Well,
week
we
we
can
have
just
the
just help
No.
travel grant.
And I do have a question.
Oh, really?
So I've actually put them,
That sounds great. In fact, I think I saw an ad for one. I might have seen an ad for that.
Yeah.
yeah, I mean, I have a question, so it's all the pets, right? So like, here is,
I've never
Friendship.
spent much time in Costa Rica. I think I was yeah.
we've got everybody in the class, there are 34 people in the class, one person doesn't show up.
Well,
I
I
guess.
spent 8 years in Brazil.
Here.
I spent 3 years in,
You know,
2 years in Argentina,
And I've got,
3 years in El Salvador, 10-year period in Guatemala, except that I was going to school in the States at the same time.
10 years.
Yeah.
You speak Spanish.
and I've got like the attribute file.
Yeah, except for the fact that it's like the
Yeah, I
Spanish
don't
of a
know, like, I've
17-year-old.
got
You
these
know, like
all
I haven't gone,
as separate files.
I haven't spoken since I left
And I
in
don't know, you know,
78.
he has a lot of files.
I get very few opportunities to speak, you know. Yeah, and I visited most places. I have not been to Colombia, and I want to go. I've been to Peru.
Okay, all right.
From what I understand,
It was, let's see, I think I must have done Cusco and Machu Picchu. And this was in the 70s, so it was like, getting up there was really difficult. I don't know what it is now, maybe there's a,
So I don't have anything.
There's a helicopter.
wow, okay.
You can hike it.
So I remember running around in Cusco, because I was with a friend, and we were just, running over ruins and stuff, and then later in the day feeling a little bit nauseated, like, that wasn't a good idea.
I mean, the citations I can handle.
And then I've been to the Galapagos, which is really a lot of fun.
That takes a while.
Yeah.
It's far out.
It's far out, yeah.
How many? You got one?
Well, I'll see.
Yeah, I went on a boat, and it was a week-long thing where we went from island to island.
It's just trying to get something like now because I want to find people.
Yeah. Even then, though, you have to then take a boat to the other islands where they don't allow people
Did you see
to.
the picture?
The,
The
oh God, yeah. They're all over the place.
So,
And the best part was
like I would
snorkeling there
expect,
because there's so many sea lions and watery iguana and stuff, and you feel like you're really swimming in amongst big things, not just little fish.
but it's also perceived success, right? Not actual success.
it is perceived everything.
I loved it. I loved it. It's so great.
You're like, they're gonna kill me.
Yeah, right.
It's all the past.
Well, one of our party was concerned, and then he passed on the State Department thing, and I was like, oh shit.
And for this,
Now, even when I was
in
there,
the attribute
there was
file,
danger, but it was targeted. It was Civil War.
So this is my
And
combined.
they bombed our building because there was a leftist newspaperman who lived in the
Yeah, and
building.
this is the thing.
They
like,
bombed that.
um,
This is in the 70s.
Organizational.
But now, there's more of a generalized crime. But back then, you didn't worry
So I
about
just
it because
added
it was
this
very
one.
specific to the combatants. But,
To get
but even now, I did not feel
But I mean, that is
Yeah.
my main.
I did not feel unsafe. I felt very comfortable, and my wife really enjoyed it.
Does she know Spanish?
A little, yeah.
Yes.
She had lived with a family in Mexico for 2 months as part of a learning Spanish thing. So, because she was an anthropology major, and so she had some Spanish. No, she got her master's in anthropology and then was ABD and a PhD in linguistics, but never finished.
Well, I mean,
Not enough.
So now she runs her software business.
I think so.
Yeah. I was gonna say it's probably not more than one.
All right, well, I should see here about this class. Lancaster. All right, we probably won't do that.
Right.
Well, to your conversation, I just wanted to show you quickly, maybe too quickly to really understand. There's a paper by Ron Burt in which he asks managers about a lot of their social relations. And these include who do you go to for buy-in on some idea, who do you socialize with, who don't you know well, who do you know well, how long have you known them, is the person your supervisor, are they your subordinate, do you see them monthly, less than monthly, all those kinds of things. And then he correlated each of those matrices with each other and put in an MDS, very much like we just did, except that ours were different time periods. These are different kinds of relations. So he wants to see which relations correspond to which. So for example, if you're close, does that mean you tend to meet weekly? And if you go to this person for buy-in, do you also tend to see them as highly valued? The answer is yes, you do. He was particularly interested in the differences between French and American managers. So he did this separately with them. And I would have to say that in general, what you see is a typical pattern of human thought, which is that you have some things here which are just distant, difficult, not well tied. And then as the relationship increases in strength, it bifurcates into two directions. One is more instrumental and one is more expressive, one more personal. The one thing that I think it was that Bert's comment was in the paper, and I really am hazy on this, I'm afraid, was that the American managers, when they walked into a company, they had already been to other companies and had other relations with the existing managers, and so they already knew before the people that were important, the people that you needed buy-in with and highly valued, so they knew before there. The French managers did not have that. The people that they knew before tended to be the people that they were personally friends with and kind of grew up as a cohort with. They had gone through school together and so on, and weren't necessarily the ones that they needed when they walked into. So I remember making some comment, like when an American manager walks into a new organization, he already knows who the key people are in order to get things done. But for the French person, it takes longer. So he was explaining differences in French managers' performance and American manager performance.
Because it's not about this data, but about mine.
Yeah.
That I have social emotional support that would be done, instrumental support, and I have also instability relations. I haven't tried to correlate them, but I guess that you can have a difficult relation with someone that you have to ask for support.
Yes, definitely. And I'll show you an example that I think really shows that the difficulty of these things. In our data sets, we have the Sampson data set. So let me start up UCINet. And I'll go to Tools, Similarities and Distances, and put in Sampson. And we'll do Pearson correlation of matrices. We actually did this last time, but very quickly. Now, the Sampson data sets, there's liking at time 1, liking at time 2, liking at time 3. There's dislike, esteem, disesteem, influence, non-influence, praise, and blame. And you see that there's positive and negatives here, but just take liking at time 3 and disesteem. It's only it's a small negative. Because, you know, it's not that clear that it's like, in a very small, closed setting like this, there are people that you both love and hate at the same time, or that you do certain things with, go to the movies with, but also don't like that much. You know, so the correlation is kind of low. And it's true of a lot of work situations where you can't get away from certain people. You have to do these things with them. I think that's similar to what you have. Yeah. So liking and dislike is only, only has the negative correlation of minus 0.168, which is kind of surprising. So in this data set, in fact, liking, the positive ones and the negative ones are not the opposite poles of each other. They're actually two separate dimensions. And I can test this by taking this correlation matrix and running a factor analysis on it. I can go to Tools, Scaling Decomposition, do Factor Analysis. The input data set is the correlation matrix that I just created, which is the Sampson PM. The type of data, it is not a variables by cases, it's a correlation matrix. It's already been computed. I'll use principal components, and I will run it. And it finds 2 factors with an eigenvalue greater than 1. And here are the 2 factors. Here are rotated. And you can see that we've got positive relations are loading high on this factor, and then negative relations are loading on the other factor. That's not at all what you would normally expect. If it were some kind of something else, attitudes or something, you'd expect one factor and things loading positively and negatively on the same factor. But that's because they are not opposites of each other here. And that's often true in human relations, especially in closed groups. Okay. Yeah. It's even better with value data, yeah. So I'm correlating here matrices that are 1s and 0s. A correlation really wants to have more variance. Exactly, yeah. And so to me, it's surprising that there should be 2 dimensions. I always thought there must be something wrong with the data. But I've come to realize in many data sets this is true. This is real life, exactly. And then I read the word frenemy, and I was like, oh my God. Okay, so now let's repeat some of the stuff that we did last time. Let's look at CampNet, and we're going to predict it over time, and we're going to use attributes to predict it. So let's take us through the whole process so you know how to do it. We started with a data set called 92. I want you all to follow along. I certainly did, because that's not the output that I was expecting. I tried to display 92. Just display it. You see that it has week 2 and it has week 3. And you know that this is a workshop. It was a 3-week workshop, and we did these things after each week. We lost the week 1 data, however. They are rank order data. We were not very good. So there's change between the 2 weeks. We could correlate the 2 weeks. I'm going to dichotomize them for the fun of it. Oh, wait, since you brought it up, though, why should I dichotomize it? There's really no reason to. Let's not. But I am going to reverse it. I just prefer to make it so that the big number means more liking. It's just easier for me to think. Okay? How do I reverse it? How do I reverse the values of the matrix? Yeah, there's a reverse command. I mean, so you could do it in the CLI, or you could do it in the transform and reverse. So the input data set is CAP92. The output data set is CAP92-rev. That seems okay. I will say okay on this. And I always check it by looking at myself, my own row. And according to this, I liked myself the most. That's absolutely true. And then I like Bert's second, 17, so that's good too. All right, the data, all right. Now I am going to separate these 2 matrices so that one is an independent variable, one's a dependent variable. So how do I unpack? That's how I do it. I unpack. I go to data and I unpack. So this is CAP92-rev. And it notices right away there's week 2 and week 3 in it. And so I say, yeah, that's fine. I go, okay. And now it's created these 2 separate matrices that are valued. And now I could run a regression just to predict week 2 from week 3, just as a starting point. And I'm going to press Control R to get there quickly. And this is a QAP regression. The dependent variable is week 3. It doesn't make much sense to predict week 2 from week 3. Week 3, and I'm going to predict that from week 2. And in terms of all the things, the options in here, the number of permutations, this is set very low, maybe 20,000. 20,000 is like publication quality. You always want to track t-statistics, which are pivotal statistics, not betas. The only reason there's an option here is for people who are experimenting with QAP methods. But t-statistics definitely work well, and especially dealing with autocorrelation. There is something called an optional partition. Permutations will be performed only within classes. Suppose you collected network data in this classroom, and then you did it in 15 other classrooms. And in no case did you ever permit there to be a tie between the classrooms, okay, because you just simply had the questionnaires for each classroom. And so if you wanted to put them all into one giant network, which is unconnected, and predict something, you would tell it to do the permutations only within the classes, not across classes, because it wouldn't make sense. Nobody could ever be substituted for somebody that's in a different class. So that's just something that you should know about. Also, there's a lot of different outputs, including predicted values, which may be useful. So let's run it. And we have an R-square of 0.55, which corresponds to a correlation of 0.74, which makes sense. Notice that these are not standardized data, but the unstandardized coefficient is identical to standardized coefficient. Anybody know why? It's because the two data sets each have 3 ones in every row, and so they have exactly the same mean and the same standard deviation. And so whenever that happens, standardized coefficients and unstandardized coefficients are identical. Just a little fact to know. Okay, and the p-value is very high. Now, sorry? That's good, and that's good, yeah. So that means this did not happen by chance alone. It's just too high. So now, what do we think might predict ties? Well, last time we said it was things like gender, right? Maybe the same gender. So let's do same gender. Now, how do we get to the same gender? Well, we can create it by going to Data, Attribute to Matrix, and the input attribute data set, well, it's a data set that's associated with CAP. If you remember, it's CAP, and it has gender, role, and betweenness. So we'll start with gender. We're going to do this thing called exact matches, which means it's going to create a new data set in which there's a 1 between 2 people if they have the same value of gender, and a 0 if they have a different value. So I'm going to call the result same gender. So we say OK. And like I said, ties between women are going to be 1s. Ties between men are 1s. And ties between women and men are 0s. So it's whether or not they are the same gender. I close this. And I press Control R. And I now add same gender to my list of independent variables. And same gender appears to be significant. And of course, week 2 is still significant, as we expected it to be. So it does seem like there's a tendency for new ties to be within the same gender. Nothing new. What if we had a more radical idea? What if this is a feminist class, and we are very much been studying the idea of a male patriarchy and so on. And what if everybody prefers to have a tie with a male? It's not a matter of being the same gender, it's just that everybody prefers men. By the way, it's exactly the opposite of real life. But anyway, so just ask any patient at a hospital, would you rather be attended by a male nurse or a female nurse? Everybody says female nurse. Constituting a major discrimination issue. Okay, thank you. Thank you. All right, so how would we test this more radical hypothesis? We can go back to data. You can go to attribute to matrix. And instead of exact matches, what we want is something like a receiver effect. A receiver effect means it's some attribute of the receiver of a tie that's determining whether ties are going to go to that person. So it's going to be the gender of the receiver. Now, I'm going to shorten this name again. So it's just receiver gender. I'll run it and then we can examine it and see what it really did. That's not what I wanted it to do. My machine is screwing up. Okay. So, what did it do? Notice that Holly is a woman, so she gets a 1 all the way down the line. Bill is a man, so he gets a 2 all the way down the line. So think about that predicting a tie. Where there's a 2, we're going to predict a tie. So since from Holly to Bill is a 2, we're going to expect that there's going to be a tie from Holly to Bill. Whereas the opposite, from Don, well, in fact, from Don to Bill is also a 2. So basically, we're going to expect ties to all the people who are on the right and not ties to people who are on the left, because they're all men. So, and what did it really do? It just copied the gender vector. It made it the same for every row. That's what it really did. But now we're going to add this matrix in, Control R. And I've forgotten now what we called that, so I will have to press the browse button. It says receive gender. Okay. So the receiver's gender is what's going to determine things here. And we can run it. And that is just not significant. Wait, it is significant in the reverse direction. So actually what's happening is that people prefer to make ties with women, as I secretly thought. And everything else is still significant. What about something more complicated? What about reciprocity? At week 2, I get the feeling that you chose me. So at week 3, I'm going to choose you back. So what we can do to create a testable effect is create the transposed matrix. So suppose I go to transform and I go to transpose, and the input data set is week 2. And that's going to create the transpose of it. Now, let's just run it again and we'll talk about it. Whoa. I don't know what's up with my computer. transpose, week 2 to transpose. Hopefully you all got this. Okay. Now I'm going to just move this to one side, and I'm just going to display week 2 side by side. So week 2 is on the right, and you can see that Holly, you could have seen that Holly has chosen Gary as her number 1 person, but in the transpose, it's Gary that has chosen Holly as the number 1 person. So I've simply interchanged the rows and the columns. And the idea is that if in the real world, let's say there was a big number from Holly to 6 here to Gracie, then in the transpose now, we'll have that same strength. How do I put it? Let me see if I can say that better. So that's maybe not a good example. Let's stick with Gary here. So Holly, and let's remember that the data have been reversed. So Holly really likes Don. Big number here, 17. And so we are going to, how do I put it? Maybe it's easier to think in terms of columns. Let's say Russ. Yes, it's easier to think in terms of columns. So Russ has sent Holly a 16. That means that Holly is going to feel like she needs to reciprocate the 16. So we're going to predict that Holly's going to put a 16 for Russ here. Okay, that was the way to put it. And Russ sent a 1 to Pam. Russ is like, I don't like you. And Pam is going to reciprocate by giving Russ a 1 next time. We're guessing. These things won't be perfect, of course, because you don't know other people's feelings. But you can get the idea when somebody puts you as their worst, right? So the transpose then provides a prediction for what's going to happen next. So I go to my control R. I add in week 2 dash transpose. And let's see if that predicts anything. Sorry? 2 things or 1 thing? Oh, two-tailed. Oh. Yeah, you know what? Two-tailed is a lot more normal. Again, as I mentioned last time, there's a tradition in permutation tests to do them one-tailed, but most people understand two-tailed better. That's my computer for you. It's just going to print something else. Okay. So it is the case that if in week 2 you scored me high, in week 3 I tend to score you high. Okay. Now we are starting to run out of data. It is 306 observations because it is dyadic data, but still we're starting to add an awful lot of variables in. But I think we could manage to get a couple more in. I want to do something radical. Like you and I will send a tie to you if we have a lot of friends in common. So, well, yeah, I was just thinking that's not quite transitivity. Yes. Yeah. transitivity would be if I like you and you like somebody else, then I'll like that somebody. But having friends in common means that if you like somebody and I also like the same people that you like, I'm starting to think well of you. I think, well, you must be okay since you like all the same people I do. So how could we get that? Well, there are specific things in UCI that we could go to network and compute structural equivalence, but I'm going to do it more simply by going to data and choosing affiliations. And I'll do it and then explain it. So the input data set's going to be week 2. The mode is going to be rows. Oh, the sums of cross products. So that's going to be weird. That's going to be weird. I forgot that these are valued data. Well, let's use correlation. That is not what I just did. Please, what is wrong with this thing? Okay, now what have we just done? What have we wrought here? Remember what? Remember what affiliations did? What 2-mode to 1-mode was all about? Sensing a now. Suppose we had person by event. And we wanted to convert this into person by person. And so we've got persons, 1s and 0s in here. And we translate that to person by person by counting up the number of events that they went to in common. So person A here and person B went to 2 events in common. So we had A, B, C, and this number right here would be 2. And the way it does it is by simply multiplying the rows and summing them up. 1 times 1 is 1, plus 0 times 0, plus 1 times 1. And so the sum would be 2. If we don't have a person by event matrix, if we had a person by person matrix, and we did the same trick, we have a pattern of 0s and 1s as to who they like, that's person A, here's person B, they like these other people. We do the same procedure, then A, B, C, A, B, C. What's the number from A to B going to be? Well, it's the number of third parties that they both liked. A liked this person, and B liked this person, so that's 1. They both liked this person, so that's 2, and then that was it, so then we're going to get 2. So in other words, the same procedure is going to count the number of persons that you both like. Now, I didn't actually choose that technique, though. I chose correlation. Because what we actually have here is strength of ties. Right? We've got a 2 and a 7 and an 18 and a 3 and a 9 and a 7 and a 2 and a 1 and a 5. And so I'm just going to correlate those 2 rows and put that here. And from A to B, it might be 0.37, meaning that, generally more or less, the more A likes somebody, the more B likes them too. It could have been for A to C a minus 0.2. Whoever A likes, C doesn't like. So we're just creating a correlation matrix of their outgoing picks. That's what we just did now by using that affiliation routine. We could have done this in other parts of the program. We happened to choose that one. Let me go back and look at the choices. We went to data. We went to affiliations. We said we're going to correlate the rows using the correlation coefficient. And the output was going to be called week 2 rows. I'm going to run it again just to see if it comes up with the same value before. Yes, it actually produces the output that I asked for. Amazing. And you can see that Holly and Brazy have very similar views as to who they like and don't like. But it's not true of Holly and Carol. I say that if I am highly with your views on the world of who you like and who you don't like, that I'm more likely to make friends with you. So let's add this to the regression. Yeah. We don't know that, actually. Yeah. I'm claiming here, though, that in week 2, we noticed that we had similar likes and dislikes, and that's going to make it more likely to choose each other in week 3. So at least it's in the future, which is helpful. I'm going to do Control R. I'm going to put in my week 2 rows and say, okay. I just have a feeling it's going to print something that's unrelated. Okay. Well, it's not significant. Okay. So for the first time, I find here that, in fact, just because you and I have similar views of the world, who we like, doesn't translate to me liking you. And partly, of course, it may be unobservable to me as to who you like and who you don't like. We could have also done it by who likes us, so that if I'm liked by the same people that you're liked by, we might have expected a stronger tie. I'm just going to do one other idea, and that is the idea that maybe you're more likely to form ties with people who are socially near you. So if I look at a picture of week 2, oh yeah, I keep forgetting that it's strength of tie here. So here we've got that men's participant group, we've got the male instructors, we've got the female participants group over here, basically. Slightly different picture than we're used to seeing because this is week 2, not week 3. Breaks up right there, I'll leave it there. I'm guessing that if Pat's going to add a new friend, say, it's going to be to somebody like Pam and not to Lee. That somebody who's really distant from you socially is not the person that you're going to be most likely to form a tie with. You just don't even run into them. So I'm going to use geodesic distance as a covariate. So I can go to network, cohesion, geodesic distance. The input data set is week 2. And I don't think we need to do any transformations, but we could use reciprocal distances so that the bigger number means greater social closeness. Yeah, I'm going to make reciprocal distances. And we run it. The result's going to be called week 2 geo. And what the hell is that? Is that what you guys got? Oh. It's because these are valued data. So since there's a value between every pair of people is tied. So what's the distance between them? It's 1. Why didn't I just dichotomize when I had the chance? So I'm going to dichotomize week 2. Oh, and yeah, okay, I'm going to dichotomize week 2. And anything greater than I don't know, a 16, a 15, something like that, will be a 1. 15, 14, I'll do 14. So the output's going to be called that mess. We just have to remember that. And now I could compute distances on this, geodesic distances. So I could go to network, cohesion, geodesic distances, and that mess is hard to remember. So I just grabbed it from there. I'll do reciprocal distances, I run it. Okay, I have various reciprocal distances. And now I'm going to throw this into the regression, and I'm going to claim, yeah, with one little modification. So network, cohesion, geodesic distance, and then I told it that I want to do reciprocal distances. So it's going to do 1 over the distance. Again, just because I think it should be line up that the bigger the number, the more closeness, the more tightness. And then it'll create that mess. And I can go to Control R, and I can add that mess. There it is. And my claim here is that it's more likely to form a tie with somebody in week 3 if they are from your general social circle and are not really far away from you. If they're proximate. Yeah, weird. Okay, and that is not significant. So controlling for everything else, it's really not the case. Now, I think that this would be the case in a large network. In a small network, obviously, everybody knows who everybody else is, and so there's no issue of becoming acquainted with them. But in a very large one, you tend to become acquainted with people who are already acquainted with somebody that you know, and you run into them because it's the same party or something like that. Okay, how are we doing on QAP? We're feeling somewhat okay. Let's do something different. Let's go to logistic regression QAP, because I want to show you the tool that goes along with it. I'm going to dichotomize our week 2 and 3 stuff. I'm going to go back to the beginning, though. So let's go to transform. Okay, so everybody go to transform and then dichotomize. Transform, dichotomize. We're not going to do week 2. We're going to do CAP 92, the original data. The output data set, let's see, well, I don't know what it's going to be yet. Let's go to the dichotomization rule is going to be less than or equal to 3. And we could leave that name, but I'm just going to make a CAP 92D for dichotomized. Okay. Now, let's run this. My computer will show some other output. No? Okay. And you see how it's got both weeks, and they're dichotomized. And again, I'm going to predict week 3 from week 2 using logistic regression. So to do that, I have to separate them. I'm going to unpack. I could do that in the CLI by simply saying something like unpack Camp 92D. And I could display one of them just to be sure. Seems to have worked. Okay. So I close. The last step was to close, but just before that was I did display week 3. So I'm going to do a little logistic regression. I can do that by pressing Control L. The dependent variable is going to be week 3, because I hate predicting earlier periods from later periods. And it's an underscore 3, not a dash 3. Week 2. And I wanted to show you that some of the effects that we've been creating are all available directly in this program. So here where it says relational effects, I could do reciprocity. And all it's going to do is create the transpose of week 2 and stick it in there. And I press add. And there it is. So that's easier than going outside, transposing, putting it in here. So these are both dichotomized because we dichotomized Camp 92 and then we unpacked that. Unless we didn't, yeah. And then we could have transitivity, which we didn't do recently. We could have preferential attachment. All that means is that we expect that there to be more ties to people that already have more ties in week 2. So this is just in degree that we're using. Very much like when we had the case where we were trying to predict, we thought that there would simply be more ties to men because they're higher status. So here we're just throwing in degree, and we're going to predict that people who already have high degree are going to get more ties. So that's good enough. Let's just run this. And preferential attachment is not significant. Now, I want you to see what preferential attachment is. So I'm going to close this. Let's display the matrix that corresponds to that. And it is week 2 preferential attachment. That's what we created when we ran this. We open it. We will see that it is just the degree vector written out, duplicated for every row. So in week 2, for example, Pam was selected to be the top, among people's top 3, 6 times. 6 different people thought that Pam was a close friend. So she gets a 6 all the way down the road. Only one person selected Bill, and that gets down the road. So where we are predicting, this big 6 here should correspond over here in the week 3 matrix to a tie. Because it's a big number, and so we're expecting that that's going to lead to a tie. In other words, we predict a high number of ties for everything in this column because Pam has a big number in it. I know that that's hard to understand. It's kind of weird, but it's how you throw in an individual characteristic into a dyadic regression. But it turns out that's not how it worked. There is no tendency for people to send ties to people who already have a lot of ties. So if I go back and look at the output that I just generated, we see that reciprocity matters, we see that transitivity matters, but preferential attachment does not. Now, what about attributes? We can put attributes in here. So I'm going to press Control L. And down below, there's a place for putting in a data set that contains node attributes. And as you know, we have ATTR. And it has various attributes like gender. And then we could choose an effect, such as a receiver effect. That's what we tried before. We thought, okay, men in general are just going to be more likely to receive ties. That proved not to be effective. I'm not going to reproduce that here. We could do homophily. So that's going to be essentially what we did before. It's going to be, it's going to create a matrix in which there's a 1 if two people are the same gender and a 0 if they're separate genders. So I will add that and then run it. So notice it created gender homophily categorical. If we looked at that on disk, it's just a matrix that has 1s and 0s in which, it's 1 if they're the same gender and 0 otherwise. So here we run it, and homophily is significant. Preferential attachment simply isn't. Let me go back, Control L. There's other possibilities. We don't have age. We do have centrality. We could have the idea that maybe difference in centrality, like you're more likely to form a tie with somebody who is equally central as yourself than to make a tie with somebody who's very much more central than you. We could try that. So that's going to be simply the simple difference in centralities between pairs of people. I could run that. And that makes no difference. And all the other results are still the same. Homophily still matters. Preferential attachment still doesn't. And difference in centrality is just not how people go about making friends. This doesn't affect it. So all of those effects are simply a more convenient way of doing what you could always do by going over to data and just creating the effects yourself over here. Questions? All right, let's have an exercise. Let's see if you can predict. Let's see, which data set shall we use? Can you predict business ties from marriage ties in the Paget data set? I leave it up to you how to do it. Business. The idea being that business relationships are embedded inside of social relationships.
Yeah. For Paget.
Oh, if you're interested in the attribute file, it's Page W, I think. I think wealth is the only one that I understand.
think that if that was a number of prior marriages.
So repeat the question again.
It was to predict business ties from marriage ties. Marriage
I mean,
from
would you
business.
not? I mean, we're doing what you just said, right?
Business ties from marriage.
Yeah. There's a general sociological principle that says that economic transactions are embedded within the context of social transactions. So the social is the independent and the business is the outcome of
Okay,
that.
so we want
Not that it can't be the other way around, but just a general thing. A classic point of view.
Right, but we're predicting one from the other, right? So, if we're predicting marriage ties, that would be.
Well, it depends on one's like, so is it like this where like a 0 equals no marriage, and 1 equals marriage, and then or you would have like no business and equals business, or is it like marriage equals marriage? Not. Well, it's in marriage and business ties. Or business. I think it's or business ties. Isn't it what? I think it's
Yeah. Right.
Now, if you want to challenge yourself, there is a data set called Page W. And the first column is wealth. And you could see if maybe somehow you tend to have business ties towards wealthy people or something like that.
I mean, we can run it.
He's underrated, yeah.
Yeah.
That poses a problem for like
You can-
Yeah, it wasn't.
Yeah, so you did it in
Right.
Yeah, so it's just a different.
Why are we removing?
So maybe you have more business ties to people whose families are more similar. You don't have a poor family doing the rich family.
Yeah. Yeah, I mean, that's what. The relational effect is this. I mean, have to accept that. Yeah, there you go. Yeah.
Let's look at it.
So, did people do something like this? I'm doing it here in QAP. You might have done it in logistic regression. It's a matter of whatever, preference. But basically, all I was asking you to do is to just predict B from M, having unpacked it first. Okay, well, you can definitely do that. And we see that it's highly significant. So I did too. This is the linear regression. And your standardized coefficient should be 0.372 as it is here. If it's not, there's something wrong. Now, the p-value might be slightly different. Oh, you did logistic, okay. So if we did a logistic, then we could do a control L here, and we have a patch B being predicted by a patch M, and we run it. And again, we get a significance. It's like, okay, marriage size and business size is highly related. We could have gone with some other stuff, adding in some wealth, if we wanted to do that. For example, since we're here in the L version, I could bring in a data set called patch W, and wealth was one of the things here, and maybe difference in wealth, but because these are undirected ties, it doesn't make sense to predict that that I will tend to send a tie to a wealthier family, and then they will not send a tie. They have to send a tie back. So really, it should be the absolute difference here. And yeah, if we had that, that would be fabulous, exactly. But we don't. So here we've got absolute differences, meaning, and I would hypothesize that families of the same wealth level would have a tendency to have marriage ties with each other, and more rarely would it be difference levels. So we run it, and we find that, yeah, I heard a group over there say, yeah, it's close enough, but I'm not going with that. Predicting marriage. Oh, business, sorry, yeah. Predicting business from marriage, yeah. So, all right, I want to give you one more chance to do some work on your own. Over on the top left, over on the blackboard, is a network data set called Crack High Tech. Inside of it is a data set called advice. I want you to predict who goes to whom for advice. You can use the other relations that are in that data set, and you can use the attributes that are in that file that it says high-tech attributes. Meanwhile, I will learn about the data set. I'm going to predict advice, which is in that crack high-tech data set, from anything you like. Yes, you will have to unpack it. And one of the attributes I see is level in the corporate hierarchy. And I would think that you ask advice of people who are high in the hierarchy.
And that would be here, right? Right.
This will be the boring part in the YouTube video. An easy starting point is to predict advice from who reports to whom. I'd probably seek your advice if I report to you. Sure. So I want you to predict advice, and the advice is in this data set that's called, over on the blackboard, you see where it says net, crack-high-tech. So that's a data set that has 3 relations in it. And these are the 3 here, advice, friendship, and reports. So I want you to predict advice using the other 2. And then you can also venture into the high-tech attributes, has things like level in the organization, whether you're a manager or not, and that kind of stuff, what department you're in. So the first thing you'll have to do is unpack the network data set so you can isolate advice. I think because it's a high-tech company, that age shouldn't make a difference, you know, because you could have a 20-year-old genius. Yeah.
Level of the receiver matters. And you're a receiver. And you're a sender. Friendship and reporting. But age of sender doesn't matter. But department sender doesn't matter. Age of receiver doesn't matter.
Friendship and report to seems to be significant.
Oh, friendship predicts advice? Wow, you got everything in there. That's great.
We regression and that's different.
Yeah.
But there are a
But
few
this
things.
is all like independent, this is all individual attributes of the node, besides just whether or not they're connected in these networks. We didn't look at like reciprocity or homophily or any other aspects of these networks that might predict.
Right, yeah.
Advice.
Sure.
So it's just basic, like if they're friends and they're also probably in an advice.
This is like bullshit.
Yeah. And reports to is clearly significant. And obviously, you seek advice from those that you report to.
I think it's interesting that really, so tenure of the sender and then tenure of the receiver and level of the receiver are all significant, but like department's not, age of receiver's not, department of the sender, level of the sender. All
But
of that
those
stuff
make
is-
sense, right? I mean, it makes sense.
Well, in a large organization, I would think department would make a huge amount of difference.
We actually only see, that doesn't really matter.
But in this one, it's so small that maybe.
That's level department. Yeah.
Interesting, because you're predicting who do you go to on an advice tie. And then again, it's just whether or not that there's a tie, not who initiates it. Because that's interesting because we see that receiver factors are a huge, or like, are a huge.
Yeah, it's not about the characteristics of the senders, I guess.
Yeah, it doesn't matter about who's sending the message, it's about who's receiving the message. But again, we don't really know. We just know that, yes, that predicts a tie, but we don't know who initiates that tie.
Yeah.
And you would assume that the lower level person, the receiver, maybe.
So you could do that. I mean, that's one of the options in there is to look at the difference in their level. And by the way, this one's negative, but I think level is coded so that smaller number is higher level.
Oh, okay.
So try to unwrap that in your brain.
I have a question real
Yeah.
quick.
The smaller number is higher level, so the higher number you get, so the lower level you are in the organization, that's more likely to predict that you may, or that there is an advice tie, which makes sense, right?
No, this is the higher level.
Well, he said lower number equals higher level.
Right.
So
Yeah.
higher number equals lower level.
Right.
So if it's negative, the higher you get on a number, which means the lower you are in the organization, maybe you're not.
The less likely you are,
Less
yeah.
likely you are
Yes,
not.
right, yeah. You got it that
Less
time.
likely you are to have.
Okay, that's interesting. Now, this one should make a ton of sense.
This is interesting, just from the perspective of the data set that I have.
I believe it.
So,
Yeah, why don't you bring in some attributes? Like tenure, you think would make a difference. I was just saying that I didn't think age would make a difference, given these are high-tech people.
this Thursday?
This Thursday. Yeah, at least at this point, I'm in the lab mostly by myself.
Oh, well, that's different.
So anytime on Thursday that you just want to pop in.
So early afternoon. I'll come in. We can talk
Yeah,
about it.
it might be one of those ones I might have to like run in.
Level.
Takes like 5 minutes, I'll take a rubber, it takes like 10, and then we're done, so I have like 45 minutes.
Right. Once I have the questions.
She was vice president, business manager.
Okay, that makes sense.
Yeah. I'm not sure, but if you have any data in there, 'cause I'm really interested in looking at, still a diagnostic population, but I kind of want to look at, kind of this individual and structural population, how that affects them as well.
Yeah.
So I want to look at that as well.
I still don't know exactly what to do.
Yeah.
I mean, this is a pre-test. I would like to do the full test in the fall, which there will be 2 cohorts. Right now, there's only 1 cohort.
Right.
So the survey went out to 34 people, right? And like I said, I ended up with, like he said, 80% is what you right? Or 86, 70%. And I was still like, great.
Oh, yeah.
Once I cleaned out all of the.
Yeah, it shows that you tend not
I want to say even the response rate is 80% is really high of response rate What do you think about like telephone surveys? Response rates for those are like 50%.
Because people,
Oh, yeah.
yeah. So, I mean, in the fall, if I do the full survey, I would do it in person, right? Like, he was like, you go in, you give a little presentation about what it's all about, you know, assure them that confidentiality and stuff will be maintained. Actually sit down, because right now,
Are you
30,
gonna have them have like Twitter surveys?
I think so.
Give them like a tiny URL or like a link page, like here's a link to the survey, and you just have to fill it out right then and there. And I feel like if you did paper surveys, like you might get some higher response rate, but that's also a lot of data entry.
But, well, it's true, that's true. So this is the survey, right? And you can see, like, when you go into Qualtrics, you get down to the name generator. And there are 34 people, so these are all my POS measures. So I've got everybody listed, and you just select, but see how long that list is? If I had 74, 75 with both cohorts, it would just be. But on paper.
That's why I would think that you might, you could potentially break it up. Didn't we talk about this kind of at the beginning of the semester? I'm sorry.
No, it's totally fine.
There, but like, so even, you know how like in our program, right, you have kind of like PhD and MA, and so then you could break it up. And then you would
Well, this
have,
is a professional master's degree program, so everybody.
I'm reporting to you,
then you'd have, you know, first
then
years,
Right, right.
your reporting to me should add the chances we have.
Which is what I would do with the cohort that I would only have.
yeah, and then even for this one, you'd have USP.
Yeah.
And then first, second. And so then you can almost bring up different lists and say, okay, here are all the first year master's students who you connect with, here are all the second year master's students who you connect with. So I wonder if in this one, even though you said it's a 2-year terminal master's program, do they have like university scholars or another option? Right, so you might even just say like, you know, here are all the first years, here are all the second years.
Right,
And you can even say, I don't know if they're different, like,
Well, see, there are areas of specialization,
yeah, specialization, so you could say here within the first year.
like
here,
this,
Yeah, security and intelligence.
Right.
Diplomacy, IoT, IoT.
and I would think there would be clusters, right?
Yeah, and then you could ask them still to do, but maybe that is just an easier way to say, okay, think about all the first years in the IoT track, right? You know, think about all the first years in this track, you know? And so just instead of giving them like one massive list, right, it's kind of a way
It's
to,
broken down.
yeah, and it's just mentally easier to do that. And then I thought we had also talked about instead of at the beginning of the semester, you go down, you have this prospects thing over here, right? Then instead of doing it like this, you might have, okay, so maybe you only focus on this first person, right? And so then you would have, okay, here's person, you know, 1A that you said you knew, that you really close with, right? Okay, so who are all the people that they hang out with? And then it would go to another screen, and right here's the second person you said.
So it's not as big.
Yeah,
Because
so
I think
it's not- it's-
some of the people did not respond.
Yeah, it's more survey pages, but it's asking them to do less at a time.
One question I
And I
had,
wonder too if making it one of those, like they can save and come back to it.
right, so
But it's not.
this is my Excel spreadsheet for when I was putting in the
Yeah.
files, right? And I had questions like, who do you think? But I mean, the matrix still turns out.
But I was like,
hey,
yeah, you could also just assign them first.
Right. So these are all
Hey, maybe
my
social discovery.
attributes. GPA is useful for graduate school, you know, I mean, there's a lot of great inflation.
I mean,
But
I don't
what-
know about the Patterson school though.
Oh, yeah.
That may be a
Oh,
different.
okay. I was gonna say, I mean, like, you know, GPA and COM, yeah. it's
Well,
pretty-
what I was talking about Dr. Borgatti, you know,
You can only report to
what you would
one
probably
person.
do for success is you would survey the faculty teaching faculty too, right? And that would be your measure of success, because you would actually, and he
Well,
said
yeah,
that's very
measures
common
of
to measure.
success, you could look at things like job placement,
Right, which I've got
Yeah, it
questions
is,
down
yeah.
at the bottom.
yeah.
So you seek advice from those people who are below.
I mean,
I mean, you
ideally,
have
you would want it to
GPA,
be
They're the
but
ones who are actually
that's not
doing stuff.
necessarily great. You could look at, I don't know, do they
Faculty
have
perception.
How the technology
publications,
really works or something. Where it
conference
reports to.
presentations.
And faculty perceptions is
Well, the person who's got to ask, like, how do you want this done? It's happening. Okay,
Yeah.
interesting.
Um,
And the level of receiver thing, that
this
holds
would all
no
be,
matter
you know,
what you do,
process
right?
for success, right?
Right.
Robust
You
thing
wouldn't
around
be
there.
like,
Okay.
necessarily. Job placement, educated publications, conference presentations, faculty ratings, I'm trying to think of anything else that we can do at school.
Well, it being 12:30, I'm going to leave. That doesn't mean you have to leave. You could just stay here, you know. I can call for sandwiches or something.
Thursday, I'll